Hi, this is my third video on doing real analysis proofs. In video number 1, I proved that square roots of non-perfect squares, if they are assumed to exist as real numbers, cannot be rational numbers. They must be what we call are irrational. And in video number 2, I proved something similar, that certain kinds of logarithms, if they exist as real numbers, are not rational. They are irrational. Logarithms where the base and the thing you're taking the logarithm are natural numbers that have at least one prime factor not in common. To prove the existence of such numbers is a tougher thing and involves something called the completeness axiom. I want to put that off here and do some things that are simpler, more basic first. I want to prove some fundamental inequalities, and in this video I'm calling it fundamental inequalities 1. There will be a fundamental inequalities 2, 3, etc. We're going to prove a couple statements here, A and B. First of all, if you've got two real numbers, A and B are elements of the set of real numbers, with 0 being less than A being less than or equal to B, it follows that 0 will be less than 1 over B, will be less than or equal to 1 over A. 1 over B is the multiplicative inverse, the reciprocal of B. 1 over A is the multiplicative inverse of A. Part B, I want to show that if n is a natural number, 1, 2, 3, 4, 5, 6, etc., then n squared is greater than or equal to n, and it will follow very quickly from part A that that also means 1 over n squared is less than or equal to 1 over n. Certain things are going to need to be assumed to do these proofs. We can highlight those assumptions. I don't really want to take a real strong axiomatic approach to these things. I want to assume that you know certain things as true. We're not going to prove those things from scratch. That's definitely something that can be done, and your teacher may want you to prove more basic things from scratch or use those things from your textbook. I'm going to assume certain things, and I'll just highlight what those are as we go. So let's look first of all at the proof of A. And before we prove the full statement of A, let me prove a smaller partial statement from A. Note that B being positive, B is greater than 0, which you could also write as 0 is less than B, implies that 1 over B is also positive. Why? Give a brief argument by contradiction. For if 1 over B is less than or equal to 0, and it actually couldn't equal 0, right, because the numerator is not 0, then, okay, here's a little trick, all right? How do we get B and 1 over B to be related to each other? They are related to each other. They are reciprocals of each other, multiplicative inverses. When you multiply them, you get 1. The number 1 is B times 1 over B. If B is positive and 1 over B is non-positive, this product is non-positive as well. This is greater than 0. This is less than or equal to 0. This would be less than or equal to 0, and that would be a contradiction. Here I am using some things that you maybe would want to prove from more basic axioms. I'm using the fact that 1 is not less than or equal to 0. It is bigger than 0. I'm using the fact that the product of a positive number and a non-positive number is also non-positive. Those are things that maybe you would want to prove more from scratch first before doing this proof, or maybe those proofs are in your textbook and you can use those things. I'm taking those as something that we can use here right away, but I'm making note that I'm assuming that you can use those things. So we've got if B is positive, then 1 over B is also positive, and that takes care of really the assumption that 0 is less than B, and therefore 0 is less than 1 over B. Now let's focus on the relationship between A and B. And by the way, a similar kind of thing if I would hold if I used an A instead of a B. So now assume, well, that these numbers are both positive and A is less than or equal to B. We must show that 1 over B is less than or equal to 1 over A. How can you do that? Probably the best way to do it, based on things that might be in your textbook, would be to focus on the difference, 1 over A minus 1 over B. If we can show that that difference is greater than or equal to 0, that will mean that 1 over B is less than or equal to 1 over A. Got that? If I can show that this is bigger than or equal to 0, that will mean this is true. Maybe in your book that's a definition of what it means to be less than or equal to, one number being less than or equal to another. And I'm also assuming that I can add these things by getting a common denominator of a times b to get b minus a over a times b. A and b are not necessarily rational. They could be irrational. But I'm going to say I know how to subtract real numbers like this by getting a common denominator. And now we can use our assumption. We're assuming a is less than or equal to b. That means b minus a is greater than or equal to 0. We also know that a and b are both positive. That means a times b is positive. Maybe, again, that's an axiom or a theorem you need to use. The ratio of two non-negative numbers is also non-negative. This is also greater than or equal to 0. So 1 over b is less than or equal to 1 over a. And those two sentences, or three sentences, I guess, take care of the proof of part A. Now let's move on to the proof of part B. We can say QED here. Proof of part B. We're trying to show really that something is true, n squared being greater than or equal to n, is true for all natural numbers. Very often, whenever you're trying to prove a statement to be true for all natural numbers, positive integers, you want to use the principle of mathematical induction in your proof. And that is a good idea here. We might want to do a little scratch work before we do this proof. Well, let's go ahead and start the proof, and then we'll think about our scratch work. Okay, so how do you do induction? You want to prove that the conclusion right here holds first for the base case. In other words, when n equals 1, note that 1 squared equals 1, which is greater than or equal to 1. 1 squared is greater than or equal to 1. That's definitely true, and not something that I want to prove from scratch using axioms, okay? 1 minus 1 is greater than or equal to 0. It is 0. 1 squared, 1 is greater than or equal to itself. So the base case is shown. Now you want to assume that n squared is greater than or equal to n, not for all n, but for some particular n. For some unspecified but particular natural number. To use the principle of mathematical induction, we must show, mathematicians often write proofs in third person. It's maybe not the best style, but it's tradition. We must show that n plus 1 squared is greater than or equal to n plus 1. If we can do that, if we can show that, first of all, the inequality we wish to prove is true for the base case, and if our assumption of it being true for some n leads to it being true for the next value of n, the next positive integer, the principle of mathematical induction will say this inequality is true for all natural numbers n. Okay? Now I want to do some scratch work over on the side. How can we show this? So here's scratch work. You don't have to turn your scratch work in typically. And it's probably a good idea to do it on scratch paper and not turn it in typically, but I'm going to do it here on the same piece of paper so you can see it more easily. Scratch work, we want to show that this is true. In the scratch work, it might be good to simplify this and see if we can see the truth of this following from the truth of this, from the truth of our assumption. We are assuming this inequality is true. This is equivalent, if we do some algebra to expand out the left side, to this inequality. In other words, if we can prove this one, then this one will follow. Subtracting 1 from both sides, this one is equivalent to n squared plus 2n being greater than or equal to n. And while that is not equivalent to n squared being greater than or equal to n, it does follow from it. There's a one-sided direction here with that one. If this is true, it will follow that this is true, since n is a natural number and therefore positive, which will mean this is true, which will mean this is true. Okay, but that basically means we're done, because I'm assuming the truth of this thing right there. So in the actual proof, now go back and say, since n squared is greater than or equal to n, and 2n is greater than or equal to 0, you could also say greater than or equal to 2, n is a natural number, 2n will be greater than or equal to 2, it follows that n squared plus 2n is greater than or equal to n. Therefore, n squared plus 2n plus 1 is greater than or equal to n plus 1, which means n plus 1 quantity squared is greater than or equal to n plus 1. And we are basically done. If you're a professional mathematician, you can just stop at this point. If you're just learning how to do proofs, it's probably good to add on another sentence. Therefore, this sounds all fancy, by the principle of mathematical induction. Principle, always I got to think about how to spell it here. It would be the L-E. It's an idea, a principle. It's not the A-L. Principle of mathematical induction. It follows that n squared is greater than or equal to n for all natural numbers n. Upside down A means for all. Now it might be a little confusing to the fact that I'm using n here. I'm assuming this is true, and here I'm using the same letter here, and I'm saying it's true for all n. Using the same letter in both spots might be a little confusing. Perhaps you'd prefer using a k up here instead of an n. So doing all what's in red here with k's instead of n's, and then using n down here, that might make it a little less confusing. But it really doesn't matter. We are done. This proves that n squared is greater than or equal to n. And both of those things are positive. N squared is greater than or equal to n is bigger than 0, right there. Therefore, by part A implies that 0 is less than 1 over n squared is less than or equal to 1 over n, although we were only focused on proving that part of it. That follows and doesn't need to be proved by induction because I'm using what I just proved and also part A for all natural numbers n. Okay, so I mean, if you can avoid using induction to prove something based on using something else, that's fine. So this is the second part of part B, I guess. I could do a little QED for that one too. Okay, so again, this was fundamental inequalities 1. There will be probably fundamental inequalities 2 and 3 for sure, I'm sure, maybe even 4, 5, 6. Lots of different inequalities are real important in real analysis. They are worth knowing how to prove and also using whenever you might need them.